Hello students, so continuing our lectures on electronic devices. So we will start our discussion with optical absorption. So an absorption will take place if the energy of the radiation is more than the band gap. So what happens is that the energy of the photon here is more than the band gap, so it causes electron getting excited from valence band. It goes to the conduction band, leaving behind the hole. And if however the energy is less than the band gap, then it leads to scattering and there is no absorption. That can take place. Now, in this case where there is an absorption taking place, where E is more than energy, the extra energy, that is E minus Eg, this extra energy is lost as heat. And this process is called thermalization. Based upon the radiation, we have a law called Lamberts Law. It says that the relationship between intensity and number of photon and wavelength is given as, let's see, the relation between intensity that is I the number of photons expressed as gamma, and the wavelength lambda. The Lamberts law relates these three quantities, and the expression is as follows: I intensity is equal to number of photons into Hc by lambda. So this is actually not the Lamberts law. So this is the relationship between I, gamma, and lambda. What the Lamberts law tells is I is equal to I0 exponential minus alpha x. So alpha is the absorption coefficient, that is the light when it gets absorbed. It has got an exponential relationship, and the exponential relationship is again governed by the parameter absorption coefficient, and its unit is in length inverse the intensity I as the unit of power, that is watts or milliwatts, and the number of photons is expressed, it is basically a number per second. So this is how the Lamberts law looks like. So whenever we have a weak illumination, by weak illumination, it has been that if at equilibrium that means when there is no light, the number of electrons is equal to the number of donor concentration, as I'll call it as P0, and the number of holes is equal to Ni square, intrinsic concentration square, by N0, and which is much greater than N0. So at steady state with light, this is what is much less than N0. Sorry. Now after we give a light, and there is a steady state attained. So at steady state, with light, electron hole pairs are generated, and extra electron hole pair generated, and they are given as delta n, which is equal to delta p. So the total n is a number of electrons at equilibrium plus delta n, which is almost equal to n0, since delta n is small, and also p is equal to p0 plus delta p, which is almost equal to p0. Now in weak illumination, only minority carriers change is considered. So in weak illumination, only minority carrier change, carrier concentration change, carrier change is considered. For example, if we have an n-type semiconductor, and which is kept in dark, so the number of holes generated in this n-type is equal to the number of holes at equilibrium, which is much less than the number of holes at equilibrium. So when we provide the illumination, which leads, that means when your H nu is greater than Eg, and then it leads to excess hole created. So if someone finds out the number of holes created due to in an n-type dark material, so this will be equal to Pn0 plus delta Pn, which is again almost equal to delta N0. So in dark, after illumination, excess hole is disappeared by recombination. So in dark, after illumination, excess holes disappear by recombination. And the carriers, they return to their equilibrium concentration. And the time for this is determined by the minority carrier lifetime. So time for this process, for this is determined by the minority carrier lifetime. And it is given as, so based upon this we do have something called continuity equation, which is given as rate of change of delta P is equal to dph plus minus delta P by tau h, where this GPH is the rate of generation of carriers, rate of generation of carriers, and tau h, it is the minority, that is the whole carrier lifetime, minority, which in this case is whole lifetime. So this continuity equation is now if the change is such that change in magnetic area concentration. That means if we have delta P is equal to GPH into tau H, so this expression we will obtain. So first of all, this is the steady state during light illumination. This represents the steady state during light illumination. That means in the continuum equation, if we somehow put d by dt, that is delta P is equal to 0, that there is no change in the magnetic area concentration, so it automatically puts GPH as equal to delta P by tau H, and hence delta P is equal to GPH into tau H. So if we solve the equation of the continuity condition, then we ultimately get the value of delta P. So delta P as a function of time is equal to GPH into tau H into exponential minus t by tau H. So this is the condition. So moving on to an optoelectronic device, we'll discuss with LED, light emitting diode. So LED involves interband transitions. And it has got a band to defect transition. And lastly, there's an intraband transition. So what we mean by all this, if we have a conduction band and there's a valence band, so whenever we have defects, say we are close to the conduction band, so we can have three different types of transitions. First of all is between band, there is a conduction band and valence band, electron hole pair formation and recombination. Then from band it can actually, so this is their defect very lying close to the valence band. So from the band it can go to a defect instead of going to the valence band. So so this is a sort of transition that can occur in LED. And lastly, the transition can occur inside the band itself. Okay, so this is called intraband transitions. So what we require for an efficient device, optoelectronic device, is we need to maximize the radiative transitions.
जी वहाँ पे एक मेरा फाइल होगा पेपर वाला, देखिए तो जस्ट कीबोर्ड की जब तो लिखना होगा,
and that means it will emit lots of photons. Now there are different ways by which an LED and by which an optoelectronic device works. LED especially works on the process of electroluminescence. In short, it's called an EL. And if you have a forward bias PN junction, PN which is forward biased, and it carries the combination in the depletion region, so it means there is a carrier recombination in the depletion region. And it generates light, so this causes generation of light. So this is how and electroluminescence and LED works. Now, if we plot the LED energy versus the intensity, so we can see that the LED spectra for that matter. So if we have plot energy expressed in packets of H nu, and this is the intensity. So according to Lamberts Law, this is alpha, so this is proportional to exponential minus E by kT. So this is basically a Boltzmann distribution. So number of photons versus energy, and so what we see is that we get a plot like this. So this is supposed to be the energy gap Eg. This is supposed to be the energy gap Eg, and this is Eg plus kT by 2. So what is happening here is that the density of states, or I should say the DOS, is proportional to E minus Eg to the power 1 by 2. So this is your Eg, this position should be Eg plus kT by 2, and the line width or the full width half maxima, this value should be 1.8 kT. So this is the emission spectrum of an LED light. So the line width, how we have achieved this, the line width for this spectrum is delta lambda. We need to find out that. We know that lambda is equal to Hc by Eg. So delta lambda is equal to 1.8 kT . to lambda square by HC. And for gallium arsenide, this is compound semiconductor, we get blue light. And it is also used the basis for white light LED. Next optoelectronic device that we will talk about is lasers. Laser stands for light amplification by stimulated emission of radiation. So what we do is normally if we have an excited level and a ground level, and if we somehow cause that to go to the excited state, it application of an energy. So this goes to the excited state. This creates electronic, creates a hole here, and after some time it recombines back. Now in this process, if we somehow manage to so after recombination gives an energy H nu, which is similar to it has been radiated. Now if we somehow manage to radiate, so while it is radiating, we manage to induce more radiation. So what we'll get, we get a coherent light coming out of the system, and this is the laser light. So and this process of allowing radiation while it is undergoing an emission process, it is called stimulated emission. For lasers to be working, there are some conditions. First condition is number one, that there should be a population inversion. Population inversion means that the number of electrons or the number of atoms is more at the high level. So usually it's the opposite. Number of atoms need to be unstable if they're in the excited state and they are in the lower level, but in this case the inversion is opposite. That is why there is a population inversion. The second postulate of laser is that the carriers in excited state, so there are carriers which are in the excited state, and incoming radiation for stimulated emission and radiation phase. We have already do it has to be in phase in the stimulated emission. So this actually completes the absorption and spontaneous emission process. If you absorb it, while it is emitting, you again throw a light on it, so we get a coherent light. And the different types of lasers that are used are different. For example, let's start with the JPN laser. So this JPN laser, this laser works on the principle of total internal reflection. intent reflection. So what is a total intent reflection? You have two surfaces, you make the light fall at such an angle that it never goes reflects outside. It is always inside the prescribed quantity, so there is no damage outside. This is the total intent reflection. And the laser works on total intent reflection. The junction, the JPN stands for the PN junction laser. It works on TIR. This is how it works. And the angle at which the laser light has to be submitted, that is called the critical angle. And it is given as theta C is equal to sin inverse N2 by N1. So these are the refractive indices and N1. The indices of the this is N2 and this is N1. Another diode apart from laser that is very frequently used is called photodiode. A photodiode is where the light is creating electron hole pairs, and the wavelength, this specific, depends on the material. Which type of what wavelength will it emit? It depends upon the material. So it's wavelength specific, and it depends on the material. So in a photodiode, the types of intercapsule transition is possible. Types of electronic transitions possible. First one, as previously explained, that there has to be an interband transition. The second possibility is the interband impurity. And lastly is the barrier high transition, or the Schottky junction transition. A photodiode is expressed in terms of categorized, whatever its efficiency, whatever is expressed in terms of the quantity beta, which is given as IPH by E into HC divided by lambda PEP, where eta is the quantum efficiency, IPH is the ratio of the photocurrent to the incident optical pass and photon wavelength. It's ratio of photocurrent at it depends upon the photocurrent first of all. Photocurrent IPH to direct open power to optic power it's called POP and photon wavelength.